here for this topic, we're going to let you get some ideas what is on the IPv6. So how popular of IPv6 nowadays? Okay, so I think start from 2019, I think around the world is about 30% of the user are using IPv6, up to 30%. But still, most of the user found that V4 is still convenient. V4 is still can be used. Why I need to change to V6? So until now, IPv6 is still not that popular. Although IPv6 is about how many years protocols? It's about 15 years protocols. But until now, you can't see that is very popular is compared to the IPv4. Okay, but because of that the fact that IPv4 are not sufficient already, it's already utilized all the IPv4 public IP address. So in this case, how we are going to cater this? Why we can not using the IPv6? Why we still stick into the IPv4? It's because of V4 and V6 are not fully compatible. Okay, it's not fully compatible. For this V4 and V6, they can communicate. They need to add on certain level of the configuration. They are not just straightforward. I can just talk to you as normal between a V4 and V6. They need to go through another layers of the transition. They need to transition before they can communicate between a V4 and a V6 address. That's why, and there are a lot of different old devices, the legacy devices, that do not support IPv6. That's also one of the reasons why they are not moving forward to the IPv6. Because when you change, you have to change all the devices that you have that to support on the IPv6. That it will have a cost that involved. So that's why V6 until now is not popular. But on IPv6, it start to popular into service providers environment. Okay, service provider environment, they start to using the IPv6. Okay, so from here, I will just give you the ideas of what are the IPv6. Okay, give you some overview of the basic protocol of IPv6, as well as what type of protocol we're going to use to perform the transition between the V4 and V6. So for this forward, so that's what I mentioned just now. As we know that the shortage of the IPv4 address resources, okay, restrict the further development of the IP technology. We need to urgently need a technology that can be replaced the IPv4. But IPv6 has come out already, about 15 years, but it's not solved this problem. Because of all the users are used to IPv4 already. Suddenly you ask all of you that to use IPv6, you found that it's pretty difficult because from 32-bit become 128-bit, that is a lot of numbers that you need to remember. So that is not that convenient. But definitely for V6, they can cater on this problem. They can solve this problem. But under the transition from V4 to V6, they take times. It's not immediate. They cannot just one night then can change to IPv6. They need to go through a few years for them to perform on the transition from V4 to V6. So for this course, we will focus on the IPv6 basic, including the background, the packet format, address classification, and also the basic protocols. As well as the last one is on the transition technologies. So this is what we are going through. So what's the address structures? So it's just similar that what you learned from HCIA on the IPv4. And now we learn on the IPv6. What are the background of the IPv6? How they distinguish all the addresses, how they classify the addresses. Like in IPv4, we have class A, class B, class C, D, E. Then how IPv6 is been classifying. And you need to know the IPv6 headers, the structures of the headers. Is it same as IPv4? Okay. And last, how they're going to go for the transition technologies. How they transition from V4 to V6 or V6 back to V4. And last, we need to know how to configure it on the IPv6. So for this objective, that is where we go into the describe the background of the IPv6 technology, distinguish the IPv6 addresses, understand the V6 basics protocols, what protocol they be using inside the IPv6, like ICMP, ARP, how they use in the IPv6, and describe the IPv6 transition technology. So 624, NAT 624, 624 tunnels, IPv4 to IPv6 tunnels, all this tunneling method under the transition. And last is how we're going to configure IPv6. Configuration on the IPv6 is not too difficult, just on the IP address method. Just have to make sure that the address, the prefix that you define are correct, okay, on the IP address itself. So on the background of the IPv6, okay, so what it mean by on the IPv6? First, we need to know on the international IP address assignment mode. So first, before we go into the IPv6, we need to know how this IPv4 are distributed to all the different regions. So for the IPv4 address assignment, it's always done by the INA, okay, globals. This is on a global and authorities. It's an Internet Assigned Numbers Authority. We call it INA. This INA, they're going to assign the addresses into these 5 different regions. Okay, IRENE, LACNIC, that is on the 5 different regions. They have a European IP, Latin America registration, Africa, and also Asia Pacific. These are the 5 different regions they are going to advertising this information. They assign the IP address to the 5 region Internet Registration Organization. So in our south, we're going to be the APNIC. This is where we are getting the address from. So from the service providers, that is called, you get it from the APNIC. So the Regional Internet Registry is IIR. It's meant for the assign the IP address to the local ISP. For example, China Telecom and China Mobile. So that is where from this region, they assign into the different big service providers. And from that providers, they only assign the addresses going to the user, going to the enterprise, going to the user. So that is how the layer by layers. INA assigned to IIR, IIR assigned to the ISP, ISP assigned to the user. So that is on the 3 layers, the hierarchy that assigning on the IP addresses. And on the 2011 February 3rd, they announced that they evenly assigned the last 4.68 million of IPv4 address to the Internet Information Center into the 5 regions around the world. So they're going to be split to this to 5 regions evenly to all these 5 regions for the Americas, Latin Americas, Africa, European, and Middle East, as well as the Asia Pacific. That is where they are going to allocate it. And this is the years they are assigned. Okay? From 2015, 14, 19, 20, 12, and 11. That is where they are assigned. So it means that right now, into INA database, they do not have any extra IPv4 can be assigned already. All the address already even allocated to all the 5 different regions. So into the IPv4, so do you know that what are the range of address as a public address? So public address, we have only class A, B, and C. So whichever is not inside the private, then it will be your public. Okay. So for the private IP that we have, on the A, you have a 10.0.0.0/8. For B, 172.16.0.0/12, and C is 192.168.0.0/16. Okay, so these are the private address range. Is for the private address. Anything other than this is all the public IPv4 addresses. So that is on how the IPv4 address assignment is allocated to all the 5 different regions already. Okay, so they already assigned. So it depends on the IIR whether they already assigned to all the different country or not. Okay, from this is on the entire region under Asia Pacific. We belong to Asia Pacific. They're going to have a lot of different countries inside. So from this country, they need to register and get these addresses from the IIR, from the region regional internet registry. From there, then they assign to all the different ISP, okay, or different country. So that is how the method of how we're going to get the address from which authorities. Okay, and for the challenge of the V4 address assignment. So IPv4 public address is already exhaustion. It's already exhausted, and the biggest driving force for IPv6 to replace the IPv4. Okay, that is the biggest driving force. It is using the V6 to override the IPv4, but that is not fully successful at the moment. It's still ongoing. That's not fully replaced yet. So even though nowadays all the small mediums enterprise are still using the IPv4, okay, they're not using IPv6. IPv6 normally it will start from the providers, service providers, or into your data centers. They might using the IPv6, but internally for the local areas, normally we just using the IPv4 because it's convenient, it's easier. We use for about 30 over years already. We try not to change because when you change, you need to make sure all the services be running. You might have a service downtime. So a lot of company or a lot of enterprise they are reluctant to adapt this IPv6 technology. They still use back under IPv4. Only to the new company they first form, they might consider using the IPv6. But other than that, it still stick with the IPv4. So the increased number of the internet user as a technology industry develop, more user are and also various type of device are connected to the public network. So it means that nowadays all the devices connecting to the internet, they must include the public IP addresses. For you to able to access the internet, you must at least have one public IP addresses. So you can see that right now the internet user are keep on increasing. So even from a 3 years old kid, they also know how to access internet. Okay, up to 70, 80 years old, they also need to access internet. So everybody are accessing internet. So how many addresses that we have is only 32-bit, and not all the 32-bit can be used for the public IP addresses. So there's a limited. So around the world population, how many billion of that we have? So in this case, how we're going to allocate every single person have one public IP address is impossible. So we need to think of some of the way to solve this. So by solving this, before the IPv6, they already have one solution. We call this as a NAT, Never Address Translation. They're doing the translation to translate multiple private to become one public, a many-to-one conversion, translation to translate your private IP to become the public IP addresses. But by using the netting, you are destroying the integrator of end-to-end communication. So it means that from end to end, you do not know where is the source and where is the destination. Because from the end to end is a private, going through the internet as a public. So that we're going to be hidden, it will hide behind of your net server. But that is also considered one of the security. Just that on the end to end, you have no ideas who from where to where. And the inabilities to adapt to the new technology, such as the Internet of Things or industry, are potential IPv6 user. So you can find that all these IoT device, how many IoT devices do we have nowadays? So anyway, they have IoT. But how this IoT can be communicated back into the server, they also need to have a public IP. But in this case, our IPv4 address is really not sufficient already. So that's why that is a potential for the IPv6 by using the IoT devices. And under the broadcast mechanism and dependency of the ARP, the leading to frequent occurring of the operating problem related to the IPv4 LAN. Because that is on the drawback by using IPv4. Because IPv4 on the V4 addresses into the local area network, they're still providing a broadcast mechanism. Whichever that I do not know, I still will send the broadcast information, especially the ARP. When ARP send, it means it's a broadcast already. When broadcast happen, let's say in a layer 2, it will just send to everybody. So this one also, it can have a problem coming from like a broadcast storm MAC address flapping will be happening into the IPv4 environment, into the LAN environment. Okay, and inadequate support on the mobilities. They're not able to support on the mobilities by using the IPv4. They lack of this function of the mobilities. That's why we're going to move forward into the IPv6. That will be a solution, but it's a temporary solution at the moment. Because right now, we are not fully converted into the IPv6 yet. For the temporary countermeasure before we fully migrate to IPv6, and this is where they come from. From the 1991, Internet Engineering Task Force launched the classification network solution to delay the time when the IPv4 address were extorted. They have come up with the NAT, a network address translation, and also support on the classless inter-domain routing were launched on 1993. But however, this transition scheme cannot prevent the occurrence of the address exhaustion, but only slow down the speed. So when the NAT, it depends. It can, right now, a group of users are sharing the same public address. But when you have multiple groups coming in, your addresses is still will out of the IPv4 addresses, because it's not sufficient for you to assign to every single group anymore. Okay, so this problem is still cannot be solved, but it just solved slowly, because by the NAT, it just slow down the speed of the exhaustion of IPv4. But one day, it still will exhaust it. Okay, that's why in the IETF proposed a next generation internet protocol, IPv6, in the 1990s. So how many years already? From 1990s until today. So it's about 30 years. Currently, V6 has become an acknowledged upgrade version of the IPv4 in the futures. So this V6 is already 30 years for technology, 30 years protocols, but until now it's not fully replaced by IPv4. Nowadays it's around 30%, 30% or 35% of the utilization compared to the IPv4. But still, most of them are still refer back to the IPv4. Since that using NAT can solve, I will just using an IPv4. I try not to change with V6, because when you change to V6, all the equipment that I'm using as a V4 have to be upgraded to V6. I cannot support any legacy device anymore. So that will be the drawback. That why some of the enterprise, they're not willing to move forward into the IPv6, because of some of the legacy devices that do not support IPv6. And even the support is also need to be extra modules and also very expensive on that. Okay, that is on the temporary counter measurement before V6 are fully replacing the IPv4. So the solution is NAT. Okay, using a network address translation. But slowly, until this, I can say that the next 5 to 10 years, this percentage will keep on increasing, because they will start to adapt into the V6 already nowadays. Okay, slowly a lot of the addresses they're using as IPv6. Okay, just like when they have no choice, they have to move forward. The use the most is considered on the service providers. Service provider is used the most on the IPv6 addresses, right? So that is on the background of the V6. Why we need to have using V6? Because of the countermeasure for the IPv4 shortage. Because we're not sufficient V4 anymore. We need to think of another way to countermeasure of the shortage of V4 is using the IPv6. But temporarily right now, they're running concurrent. NATing and V6 running concurrent. Okay, both are using to countermeasure on the IPv4 shortage. So under IPv6 implementation, we have a packet format, address classification, and also basic protocol and transition technologies. So we're going through one by one. The first one is on the packet format. How the packet format look into the IPv6. So inside the IPv6, we have a vast address space. So what is the address space that we are using on IPv6? Okay, so it's about 2 power of 128. Okay, 2 power of 128. So it means that the possible address is about 4.3 billion times 4.3 billion times 4.3 billion times 4.3 billion. Okay, 4 times of the 4 times 3 billion possible address, it become the 2 power of 128. The number, we never used this before. It's under zillion. Okay, so they have a decillion under the under zillion of the addresses. How many zero in total? I cannot count in total how many zero behind of this 2 power of 128. But there is just a lot. So the addresses compared to V4, definitely this address you will not get XOR. You will not easily out of IPv6 address. I think if in another 50, 100 years, the address is still not able to finish for the IPv6 address. Okay, so that is the features on the V6. They have a huge address space because from 32-bit it go up to 128 bits. Okay, to make it not easy to exort. Okay, they can be keep on using for the next 50 years or 100 years. And this IPv6 is a simplified the packet structures. Compared to your IPv4 structures, V6 reduce whichever is non-necessary. They will throw out some of the information from the IPv4. Okay. Later we look into how the packet format it look like inside the IPv6. So whichever is not required, they will remove from the IPv4 headers. So the header will be similar, but they will just simplify the headers. Like, remember that in V4 we have fragmentation, but when you go into the IPv6, the fragmentation will be removed because they know that fragmentation is not compulsory; it's an optional. So it's only when I'm required on the fragmentation, I only add on the headers. They make it as a modulus on the IPv6 packet headers. I add the modules when you require it. When you're not required, it just remove the headers. Okay, that is on the simplified on the packet structures. Later we go more in depth on that. And they support on the automatic configuration and the readdressings. So they can support on the automatic address configuration to allow the host to automatically discover the network and obtain the IPv6 by themselves. So they have two methods. They can be using the classless or classful. Okay, they can be based on using the DHCP, or it's a stateful or stateless. DHCP, or they're using their own auto configuration mechanism. They have two ways: stateless and stateful. Stateful auto configuration. Okay, stateless or stateful. This also we're going to cover in later part, that I will cover how this automatic configuration of the IPv6 address from the host to get the IPv6. They can get from DHCP, also can get from direct from their environment. Okay, based on their auto configuration mechanism, they can easily get this information. And next one is on the hierarchy network addresses. So because they have a vast address space to allow for the hierarchy network design, you can make it very detailed of the classification. This is based on belong to the global unicast and which region you belong to, which area you belong to. You can classify multiple portion between the columns. You can specify where this address from. You can classify more in depth into this case. And also you have a end-to-end security can be supported. Okay, end-to-end security, it means that inside the IPv6 headers, you also can provide the IPsec. Okay, IPsec authentication or encryption, it be inside the IPv6 headers. So you do not need to depend on your upper layer of authentication anymore. You can have your own IP layers encryption or IP layers authentication under the IP headers. So you can add on this IPsec into your end-to-end securities. So it means that it'll be more secure compared to V4. V4, I send everything as a plain text. For me to encrypt, I need to go on another tunnel method or using application layers to encrypt the information. But for using the IPv6, they have a function, they have option for you to provide the end-to-end security by using the IPsec headers. Add on the IPsec header inside your IPv6 packet format. So I will just add one extension packet into the IPv6 to make the message secure. Alright, this is on the end-to-end security. And the next one is a better support for the QoS. Okay, better support of the QoS. For the QoS information over here, they allow more in-depth of the classification. They call this as traffic class, as well as they have the other one is called flow labels. Flow labels. They have one specific field is called a flow labels. So later, next page, you will see that where is the flow labels. The flow labels enable the routers to identify the packet of the same data flow or provide the specific processing. So they're going to tell you that either this data is under the same flow or not. Let's say it's the same flow, do I have the same QoS value? Okay, you'll be more detailed and more enhanced into QoS value for IPv6. All right, and on the mobilities. For mobilities, because extension headers such as the router headers, destination option headers are used to make the IPv6 provide a built-in mobilities. So either that is meant for routers or this is meant for the destination. They're going to add on the multiple extension headers to make it mobilities for the IPv6. But that cannot be done on the IPv4. Okay, so based on this V6 technology features, this is just a general features I'm going through. Later, we're going to go through one by one. What are the address space that we're talking about? How the simplifying these packet structures? What type of things that simplify arrays? So from here, this is the first thing we look into on the basic headers under IPv6 packet format. So for the packet format over here, you can see that IPv6 packet contain only V6 packet headers, multiple V6 extension headers, and the upper layer protocol data unit. So that is just a basics header. Basics header is only up to 40 byte basic headers. Below here, you can add on the extensions. You can add on the extension header below on the after the destination. You just add on the next header, next header, next headers. Okay, now this is how we add it in. So from here, inside the basic headers, we have a version. This version is version 6. Okay, either version 4 or version 6. The traffic class, this traffic class, it will be just like the type of service. The type of service compared to the IPv4. They were just changing the name and set the different location. They just changed the name. The traffic class is just 8-bit long. It is similar into the IPv4 traffic on the top type of service in the IPv4. They're using the QoS. And this is the new added flow labels. The flow labels, they're going to have this bit, this 20 bit is added to differentiate the real-time traffic. This flow labels and the source IP address identify a data flow. Okay, intermediate device can effectively differentiate the data flow based on this field. Either that's where they are sending through, where is the source coming from. Are they the same flow that what they sent earlier on? They're based on the flow base. They have a flow labels to identify this information together with the source IP addresses. So I know that this is come from the same addresses. I just have to check on the flow labels. And the payload length is the same, just changing the name only. The next headers, hop limit, source address, destination address. This one is remain. This one is just that last time it called as a TTL, a time to live. And the next hop, last time this one it called as a protocols. The protocol for my next headers. Okay, what's the protocol into the IPv4? So maybe I can just show you. I just open up the v4 packet headers so you can see the compare between these two. Just let me open up this first on the IPv4. hold on, let me just open up CIA. So far, at the meantime, do you have any question? Yes, a question you can ask now. All right. So that is how the IPv4 packet header it look like. So it's 20 byte long, or it can go up to 60 byte. Let's say you have any IP option from here. So for these IP packet headers, you can see that they have a same version. The time to live they will change the name already. This is on the next headers. This is on the DS. This is on the type of service, and this is the payload length. Oh, sorry. This is the header length. Payload length, it should be this one. Okay, total length. So they have source IP, destination IP. But this one, they have been removed from their IPv6. When you compare this one and the V6 that I showed just now, okay, so that is where they are limited already. Payload length, next headers, version, traffic class, throw labels, hop limit, source address, and destination address. That's all they were added in only. So that's why you can see that they try to make it simplified. It's only up to 40 byte. Because of IPv6 using 128 bits, that's why they need to have slightly more headers compared to 32-bit IPv4 headers. Okay, so you can see just now for this is only 20 byte. For this is only 20 byte long, but for IPv6 is 40 byte. They try to reduce, but because of the source and destination address, it will be 128 bit already. So they cannot be shortened to 20 byte. So the less it be on the 40 byte they can go up to. Okay, that is how the packet header is look like. So and this two is always is 128 bits. Okay, 128 bits. 128 bits. Okay, from the source IP and also the destination addresses. So this is under the basic headers. So far okay. So you can see that on the next headers, this is on the how what they're carrying on the next headers. So this is on the next page to give you more ideas of how the basic headers and also the extension headers. So this next headers, you tell that, oh, I have another extension headers. Okay. Inside the extension header, you also have another extension headers. You can accumulate multiple extension headers to increase your capabilities of IPv6. And this is how they show from here. The extension header is optional. The data sent at the corresponding extension header only when the function of the extension header is required. It depends. Let's say you need to add the extension, then you just go ahead. Otherwise, by right, let's say you have everything it's just normal IPv6, they will just direct shift to the payload, either it's a TCP or UDP. Go to your layer 4. So it means that either you are sending TCP traffic or sending UDP traffic or sending ICMP traffic. Then they just refer back into the payload. Okay. Let's say you do not, you're going to have any extension headers. You need to figure out inside the next headers what information that you're sending. For the next headers, what is belong to. So it can be a routing headers or fragmentation headers or authentication headers you're going to add that in. Okay. Next header indicate the next header with the length of 8 bit, and the function of this parameters is the same as the next header in the basic headers. Okay. This headers and this headers is the same information. Okay. It depends on how you're specifying the relationship in between these two. Okay. So that is how we're defining on the next header information. So we need to know what information that can be added in based on using the next headers. All right. So next, that is on the payload itself. Okay. The last will be a payload. Let's say you do not specify this is the payload. So for this, inside is the next headers again. So you can have multiple next headers. So what are the next header including inside our extension headers? So we have a type of the extension header we can add it in. So we have a hop by hop option headers, destination option headers. Sorry. We have a routing headers, fragment headers, authentication headers, encapsulating security payload headers. So these are all the external headers we can add in into the IPv6 packet format. So that you can be extra header we can add in. So it depends on how and what you are sending. And this is information is required for you to add in or not. Okay. So it's just up to how you specifying the information into. So far, okay? So for the headers, you're going to add on the extension. Extension header hop by hop, destination, routing, fragment, authentication, and encapsulating. But when you're adding the headers, they must be in the sequence. They must start from top to bottom. Hop by hop option, destination option, routing headers, fragment headers, authentication headers, and up to the encapsulating the security payload headers. So from top to bottom. You cannot say that they will add first add this, second add this, then third you add this, and fourth you add this. So when you add the next headers, it always must be in sequence. Okay. So it means that when you have a header value of 0, I know that your next header is using hop by hop. Like this. So this one I will show it as a 0. Means that my next header is hop by hop headers. From this hop by hop headers, the next is 60. So I know that what is the next header. Next header is the destination option headers, and so on. So I'm going to put whichever headers information behind. Okay. So I have a 0, 60, 43, 44, 51, and 50. For the hop by hop option headers, this option specifies sending parameter for each hop on the transmission path. Each intermediate node on the transmission path need to read and process the field. And the application scenario include jumbo payload, router prompt, and resource reservation. That this is what they're going to be include. Let's say they are sending on the jumbo payload or there's a router prompt, they're going to be set this hop by hop forwarding, hop by hop option inside the headers. So it means that the next hop will be the routers. And destination option headers. This headers is carrying the information that only the destination node of the packet process. Currently, this header is used for the mobile of IPv6. Okay, you're using mobile, then you're going to add this destination option headers. For router headers, it means that they're going to use the header to specify the intermediate routers that a packet must be passing through on the way to the destination. This option is similar to the loose source and the recorded route option on IPv4. Means that you tell the traffic you must passing through this device before you reach the destination. So you need to pass through these routers. So I need to put the router header inside to say that, oh, these routers are passed through already before I can route to the destination. So they need to make sure that inside the IPv6 headers, you need to include the routing headers. They pass through these routers before you go for the next hop. Okay, you need to define which router they must passing through. It's on the routing headers. So fragment headers means that you need to fragmentize. When your packet size is too large, okay, it exceeds the maximum transmit unit. So for the maximum transmit unit is 1500. Anything more than that, I will fragmentize you. I will fragment you to multiple fragments and send to the destination. So in this case, you need to add on the header 44 to just perform the fragmentation. Okay, but this fragmentation is happening on the source. Okay, on the outgoing. On the intermediate device, they're not doing any fragmentation because into the IPv6, they're using the path MTU. So from the source to the destination, they are correlating the path MTU. This is 1005. Every source and destination agree we are using 1005. Okay. So when I fragment stuff from my side. Let's say in the meters, they have someone is using 1004. Then I have to reduce myself to 1004. Okay. I have to change my value to 1004 in this case. Okay, so they need to do negotiation first on the path MTU. From the path, it means that from the source to destination, they agree this is the MTU we can use. So for the intermediate equipment, they do not do any fragmentation. Fragmentation is only from the source, and defragmentation is on the destination. Okay, they combine the message again on the B. A is just fragmentized. Okay, when they have exceed the MTU. So it's only from the source you will see the fragment headers. That the rest is just forwarding. And the next one is on the authentication headers. So they can set authentication, they provide authentication, and also integrity check, packet ND reply function under the IPv6 basic headers. So they can set on authentication, just like in the OSPF. OSPF, you do authentication on the IP layer as well, on the OSPF layers. But under IPv6, the OSPF v3, authentication, no more. Authentication, you have to done inside your IPv6 headers. Okay, IPv6 headers to perform the authentication. Okay, you do authentication from your IPv6 headers. Or you can perform the encapsulating security payload. For this is on the IPsec encryption. The header provides the same function as the authentication header plus IPv6 packet encryption. Okay, they're going to add on the encryption. So this is more into the IPsec encryption can be done from source to destination. So this is all the extension header that can add in inside your IPv6. So this is optional. This all is optional. Only you use, you add it in. Otherwise, I do not need that. I only send this 40 byte. That's good enough for me to send the traffic to the destination already. Okay, that is on the basic headers and extension header we have inside the IPv6. So that's why that it be more flexible. When without any extension, it be very small, only 40 byte. With the extension, then they keep on increase and increase. It depends on every single packet headers they belong to, how many byte they have. There can be a 10, 20 byte, okay, difference. So it depends on what type of header type that you are forwarding. So far, okay, for this on the type of extension headers. So far, any question? All right. And the next one, we look into the address classification. How we classify the IPv6 addresses. So they already have pre-classified some of the address structures already. The classification is not like that simple compared to the IPv4. IPv4 straightforward is a B, C, D, E. They're class A, class B, C, and D and E. So, but for the IPv6, they have a lot of extra address that you can define. So in this case, we can't perform it just a basic one. So we need to know what are the differences of address classification. It's been done by the IPv6. Okay, so let's look into this one. The type of IPv6 address. So we have a IPv6 address. One thing need to be highlighted over here is under IPv6 address, they already removed the broadcast. They only left the unicast, multicast, and they added in anycast. They have no more broadcast address inside the IPv6. So it means that they are not sending broadcast by using the IPv6 address. That is where they are solving the problem that just now I mentioned on the IPv4. IPv4, every time when you go to the LAN environment, you have a broadcast environment already. So you have broadcast storm, link flapping. But using IPv6, that can be avoided because no loop will happen, no broadcast message can be allowed under IPv6 environment. Okay, so in this case, for IPv6, we're going to come out with the unicast, multicast, and also the anycast. So I think that unicast is straightforward. Unicast is just that it's one-to-one. Okay, from one to one, I will just send one copy. Let's say I have multiple point to point, I send multiple copy. Okay, that is on the unicast. So it's identify a single interface. A packet sent to unicast address is delivered to the interface by that interface. So it's just to that destination. But for multicast, it's sent to a grouped. A identifier for a set of interface, a packet sent to multicast address is delivered to all the interface identified by the address. Only interface that are added to the corresponding multicast group can listen into these addresses they send. Okay, they need to specify where is your multicast addresses. Okay, only whoever listening to this they receive. Whichever is not listening, they will not accept the information. Is that okay? That is on the differences between unicast and multicast. Sorry. So the next one is on the anycast. This anycast is added in the new method of the forwarding traffic. For this anycast, it will be happening inside the IPv6 as well as when you talk about multicast later part, they also have anycast addresses. Anycast addresses, it means that they identify a group of the network interface. They identify multiple interface that using the same addresses. A packet designated for anycast addresses is sent to the interface that to the nearest to the sender in the interface group. So it means that they're going to have multiple routers having the same address, make as a group. Yeah, equals an interface group. Inside this anycast address, they will go to the nearest. When the traffic is forward, I go to the nearest anycast for me to reach to the destination. So it means that I to simplify, I do need to travel very far away to another region to just go to this as a next hop before I can go. So I go for the nearest next hop, and this next hop you'll be having the same addresses, like something like this. I have A, B, C. Okay, I do it like this. Okay, so this is my network environment over here. I have a H device, router A, router B, router C. So from here, they're connecting another environment. Okay. All right. So in this case, ups. Let me redraw again because I forget I just using the whiteboard. Okay, let's say right now over here in the between I have a lot of different devices I connecting from. Okay, so from here in this case I will say that give me a second. Sorry about that. Let me just make it proper. Let me just draw it properly to make sure that you understand about on the anycast. Okay, this is better. So let's say I have a PC1 and PC2. I want to access the information behind here. Okay, I want to get the information behind. There's the information behind from here. So in this case, let's say you're using Anycast. I'm going to specify the Anycast from here. Anycast for this are defined. This is the Anycast. Yeah, that is the Anycast. And this is the Anycast. Okay, I using Anycast using on the IPv6. I will just assign one numbers. Okay, let's say this is a V6 addresses. I have a 2001 A64. When this is the Anycast address, all the address will be the same. 2001 : A64 and 2001 : A64. Okay. So every single one is having the same addresses when it's Anycast. So in this case, when the user accessing to the information, I'm going to figure out where is my nearest Anycast address. Okay, where is my nearest Anycast address? Definitely, this Anycast you cannot just run standalone. You're running together with the routing protocols. Okay, with routing protocols. So it means that you need to using OSPF, V3, IPv6, ISIS, and so on. So you need to work together of this. So in this case, when the PC sent to the router, you're going to decide where is your nearest Anycast go to this 2001 : A, 2001 : A. So it could be this path or could be the other path. So that is on the Anycast address. Anycast address means that they have an interface group having the same address among multiple devices. So they need to be communicate between these two. They need to have a relationship on telling that, oh, you and me are getting the same addresses. We are inside the same interface group as Anycast addresses. So we are having the same purpose. We're doing the same purpose that we are the same. So in this case, whichever traffic that I send, I can go on the left or go on the right. When left is not available, then I go for the right. Because this is my second nearest. This is the first nearest, second nearest. When this is go down, I go to this direction, the third. So in this case, it gives you a redundancy of the connection, and it better way for you to control the traffic will be always to the nearest next hop. They will not go for the largest next hop by defining the Anycast addresses. Is that okay? Based on this Anycast explanation, is all right? This is what you may call as Anycast addresses. Okay, we'll come back to this. Okay, so Anycast address is a packet to send to the nearest interface that identified by the Anycast address, and depending on routing protocol. So you need to work together with the routing protocols. You cannot run standalone for the Anycast. You must work together with the routing protocol, like OSPF v3 or using the ISIS IPv6. Okay, and for IPv6, there are no more broadcast address. When they say it's no more broadcast address, then we have a question mark over here already. When no more broadcast, how the ARP being forwarded? That is a question. That is the big question mark. Because for us to forward the data, we need to grab the layer 2 information before we can encapsulate the layer 2. But without ARP broadcast, how we can get the destination MAC address? That is the one question mark that we need to figure out. How they can getting the addresses not using broadcast. Which method they are using? That is what we need to look into. Definitely they have their solution. Later I will show you that what are the solution they're using to provide this on the how they're going to control based on ARP. How they're going to use another protocol to replace the ARP method. Okay, later we need to go into it. Right? How this ARP is being sent using a unicast, Anycast, or using a multicast. That's what we need to look into later part. Because without broadcast, the ARP cannot send. Then we cannot send. I cannot get my address. Packet cannot be forwarded as well. So that is the things, the question mark you need to remember. Later I need to explain to you on how they replace the ARP. Okay, and inside the IP addresses under unicast address, okay, we have a unspecified address /128 loopback address /1128. This is just like 127.0.0.1. Okay, this is your loopback self-loopback interface. Okay, loopback address is a 127. Link local addresses, global unicast address, and unique local addresses. Okay, what it mean by the link local addresses? When link local addresses compared to our IPv4, do you able to link what type of addresses that belong to link locals? So global unicast is just like our public address, public IP. Okay, IPv4. Unique locals, okay, just IPv4 private IP. So what are the things that can match the link local addresses? Okay, link locals, it be similar APIPA, APIPA. So do you know what this is what's the meaning for this? It's called automatic private IP assignment. Automatic private IP assignment. When you get this APIPA address, I'm not sure do you aware of this or not. If sometimes you see your IP address, let's say you cannot get IP from DHCP, you're going to generating the APIPA address start from 169.254.x.x. That is called the APIPA address. This address can be used within your local area only. It's called APIPA address, automatic private IP assignment. Okay, that is 169.254.x.x. Okay, similar to the link locals, this one is only workable within your link. Okay, only within the link you can use the link locals. Similar to the APIPA, whichever inside the local area, you can use the 169. So it means that this address is not routable. This address is not routable. This address is not routable as well on the public. It's not routable to the public network. And this is routable through the public network for the global unicast. So this is a unicast address classification that we have. So we have a unspecified, loopback, link locals, global unicast, and the unique locals. Okay, it's a FC002000 : FE80 : and also : 1 and : So that is the addresses. So you can see that behind here they have a 7, 3, 10, 1 to 8. All this number is represented as a prefix. Okay, the prefix. So it will be very similar that we write it down as 192.168.1.024. That is on the prefix as well. It means that the first 24 bit as a network. This same thing to this, the first 7 bit as a prefix. That is what it means from these slash numbers. Okay, this is on the type of the IPv6 address. So far, okay? Any question up to this point? And now we look into the unicast address, IPv6 unicast address. This one is just similar to the IPv4 public addresses. Okay, so yes, questions? Does someone have any questions? Hello? Anyone, any questions? No, I just continue in this case. Let's say you have any question, you also can WhatsApp, or you can just voice out, or just raise your hand and voice out. All right. So under global address is aggregatable global unicast address can be aggregated. And this global unicast address is similar to the public addresses. What they provide over here, they have a prefix, subnet ID, and the interface ID. Okay, let me log what's the questions. Okay, so there one question asked that from Hendik, they asked that what are the minimum? Let me just like open up the WhatsApp. What is the minimum models of the devices? Is it minimum type of the Huawei router can deliver IP solution? So actually all the routers that we have on the router side, we call it as AR routers. Okay, start from AR routers, they should able to support IPv6 already. The AR routers and also any routers. All these routers actually they can support IPv6 nowadays. They do not have anyone that cannot support, because the latest routers they already do support on the IPv6 solution already. So you do not need to worry. Let's say you're getting a Huawei device, you don't need to worry they cannot support. They can support, just that whether these features, do they need to include the licensing or not? Do they need to purchase the license for these features or not? Okay, that's what you need to be aware. But definitely they can support IPv6 already, but whether do they have any license tied together or not, then that is a different story. But for AR, NE, they all do support on the IPv6. So that's why later when we configure, we're also using this AR device to perform the configurations. Okay, they can support on the IPv6. Okay, am I answering your question, Hendik? Is it this what the question they will ask? All right, thank you. All right, so on this V6 unicast address, they divided to the prefix and also interface ID. So from first, they have a global routing prefix, followed by the subnet, followed by the host. So the address is start from 2000 colon /3. Okay, 2000 colon /3. So it means that the first 3 bit must match. Okay, 2000 colon /3. The first 3 bits. How to get the first 3 bits from here? 2000. This is 2 bytes. In total, 16 bits. Okay, it only has 16 bits. 0010. Okay, 0000. 0000. So this is a 2000. This 2000. So the first 3 bit, this need to be matched. Okay, when it start from 2000, anything start from 2 is represent that it belong to the global unicast addresses. Okay, global unicast addresses. So this is what is mentioned from here. Generally, the value is at least 48 bit. Currently, the first 3 bit of the every single assigned global unicast prefix is 001. Therefore, the prefix for this will be 2000 colon /3. Okay. For the subnet ID is used by the organization to construct a local network, which is similar to the function of the network ID in the IPv4. So you can do it like this. Let's say I have a router A connecting to router B. The address I set over here, I can say that is 2000 colon AB colon 64. So I can do it like this. So this AB is belong to router A and router B. Okay, double colon means all are 0 and 64 prefix. Okay, the maximum 64 bit of the subnet ID can be defined, and the host will be the host ID. So like this, in router number A, this is the address. It will be 2000 colon AB colon A /64. For router B, this is the address 2000 colon AB colon B 64, something like this. Okay, this B will be the addresses, the host ID that are defined. So because the host ID, you can make it complex or simple. in this case, I just make it simple. A is A, B is B. That's simple. Okay, that is on the unicast addresses. 64-bit in front, 64-bit behind. Okay, also the subnet ID you can also cover up to the interface IDs. So let's say you do not need to have that many of interface, you can also occupy the interface ID for the subnet bits. Okay. So the next one is on the link locker addresses. Okay, link locker addresses. When IPv6 run on a node, a link locker address is automatically assigned to each interface of the node, and this address is used to communicate with the other hosts on the same link. Okay, that is how they are differentiated. They only use within the same link. It means that when router A, B, and C. So in this case, router A, I have one FE80. Router B, I have one FE80. This is communicator. And on this interface, I have another FE80, FE80 to communicate. So only communicate within the link. Let's say you are using this method, A, B, switches connect to the C. Then the FE80 can be communicated between A, B, C. Okay, that is the way of the how they can be communicate only on the same link. Only on the same link. So a V6 link locker address can be used for communication between the node on the same link and is widely used in the neighbor discovery and the stateless address configuration. This is how they're going to doing the address auto configuration by using the link locker addresses. And this way I'm going to be show you. They start from FE80. So FE80, 10-bit. So how are you going to convert this to become binary? F, okay, E80. Actually, over here is already defined. F is 41, E is 31, 8 is 1000, then 000. Okay, that's the addresses. So in this case, I'm going to be 10-bit. Okay, 10-bit is up to here. That they need to be matched. So it means that it's always is a FE80. That is a 10-bit that need to be referred to for us to get this information. When you know that this is FE80, it always belong to the link locker addresses. Each of the IPv6 interface must have a link locker address. Okay, must have a link locker address. Okay, by default, they auto-generated these addresses. Later, we can go in depth how this link locker address will be generated. But for every single unicast address, they should have this. Okay, they should have the link locker addresses. Is that okay? So far, up to this point, is all right. This is just like, as I mentioned, this is just like your RB bar. Automatic private address, private IP address assignment. Okay, it's a similar stuff, but it can only use within your network. So in this case, A and C, they cannot communicate using the FE80. They cannot communicate using FE80. They need to use a routing already between router A and router B. When there's no physical connection, the FE80 is not being created, and they cannot communicate between them. So far, okay? That's on the link locker addresses. And the next one is on the unique locker addresses. Under unique locker addresses, to replace the link locker address and ensure locker address uniqueness, RFC 4193 define the unique locker address. This is just like the private IP, private address. Yeah, used within your private network. Okay. The unique locker address to prevent problem caused by the disclosure of the IPv4 private address to the public network, they generated all this. They have a FC00, and the prefix is divided to the two parts. Can be FC00 : 8, and the other part is FD00/8. So they have these two as a unique locker addresses you can define. Okay. So for this is a prefix. They have an L bit over here. The L bit is set 1 if the address is valid within the locker area, and the 0 is reserved for future expansion. It means that the bit over here is always have 1 bit. Then you can assign the global ID, subnet ID, and interface ID. Remember, For this FC00, the unique local address, you cannot be used out of the WAN. You only run within your local environment. That is on the unique local addresses. Okay, any organization that does not obtain a global unicast address from a service provider can use a unique local address. Okay, and this unique local address are only routable within a local network, but not the internet. Okay, only a local area. So it's just similar into the private addresses. So that is on the range of FC00::/7. And that are the rest of the special address that we provided from here. We have a unique unspecified addresses. These addresses is used to the source address of the some packet, like the neighbor solicitations, packet sent during the duplicate address detection, or request packet sent by client during the DHCP v6 initialization. Is to tell that I do not have any IP address. This is what I'm going to send you, 0000. I'm going to send to you that I do not have addresses right now. Do you have any address you need to provide it to me? Yeah, you send to me. So that is called the unspecific addresses. And for the loopback address, this is called the loopback test address. As I mentioned just now, it belongs to 127.0.0.1. Okay, that is the one. Okay, so you can have column 1, column 1, 1 to 8. So it's just like a local loopback to make sure your V6 are enabled, is running on this. And the last one is on the IPv4 compatible IPv6 addresses. In the transition technology to make the V4 address more important, and V6 address format with an embedded V4 address is defined. In this format, the V6 address part is hexadecimal, and IPv4 will be in the decimals. And this address is almost no longer used anymore. So because they're using a method of the how it defined. This is a method how they're going to convert your V4 to V6. Okay, how to convert this V4 to V6. But this one is normally we are not utilized anymore, no longer used. We're going to use other methods to compatible with the V6 and V4. We have later we mentioned on this. What are the way of how they're going to be communicate in between? Okay, so for a method of generating an interface IDs, how they creating the interface IDs? Let's say you are getting from DHCP or getting from the stateless auto configuration, you require to get an interface ID. You need to get interface ID as your IP addresses, as the host IDs. So the interface ID is 64-bit and is used to identify an interface on the link. And the interface ID must be unique on each of the link. Okay, like A, B, C, D, or 1, 2, 3, 4, 5, 6 is up to how you define. And you can manually configure the interface ID, or you can generate it through the system software. You can by using the EUI64 format. You can configure manually. Manually configure is set the interface ID yourself. Like I'm going to set like this is 2001::A 64. This is my address. Yeah, this is the host ID, the interface ID I define. Or you can automatically generate it through the system software, and this method is intended to protect the privacy of the host. So you can create it by using your system software, or you can using the EUI64. So you can see that, let's say right now you open up your command prompt. Okay, let's say open up a command prompt and you do this as a IP config/o. So you found that this is my link local addresses. The link local addresses behind all this information is random numbers. The random numbers they provided to me. Now this is on the system generated. The system self-generated for me, the system software, the Microsoft, the Windows, they're going to have this generation of the interface ID uniquely only for me. They go across a calculation. Yeah, calculation based on what is your MAC address. They come up with this as your interface ID. So this is called the software system software generated. Okay, and from the last one, using the IEEE EUI64. This method is most commonly used on the routers. Okay, routers. They're using on using this EUI64. Like Huawei are using this EUI64, and how this EUI64 are generating. Okay, the 64-bit format. How they're going to convert this information. So from here, that's how they're going to be include this information into our MAC address. Let's assume that this is my MAC address. My MAC address is 00123400 ABCD. This is my MAC address in the hexadecimals. When I convert this become to the MAC address into the binary, okay, 0, 0, 12, 34, 00 ABCD. Okay, this is a 0, 0, 1, 2, 3, 4, 00 A, B, C, D. So over here, how many byte that we have? So in total, you have 6 byte. Okay, we have 6 byte. 6 byte. After that, we're going to add FFFE into it. Insert the FFFE. This is the what we call as a EUI 64. Okay, we add this FFFE into between of your MAC address, between the 3 byte and 3 byte. So between the vendor code and between your interface IDs. Okay, in between I will add, because as we know that MAC address, so they have a 3 byte and 3 byte. This is on the vendor code, and this is a serial numbers. Okay, 3 byte, 3 byte. So they add in between, add the EUI64, add the FFFE. This is what they added in between to support this. So in this case, I will add in this, it will become like this. So I have this address, 0, 0, 1, 2, 3, 4, FF, FE, 0, 0, A, B, C, D. So that is what I'm getting. And also, they will have a UL bit, a universal and local bit going to be shift on the first byte, 7 bit. Yeah, 7 bit negated. So when they're doing the conversion of the EUI, they will first check on your bit number 7. When your bit number 7 is 0, they make it to 1. When it's a 1, they make it to 0. That is called the universal and local bit shift overs. Okay, they shift between 0 to 1, 1 to 0. When they shift this bit, then this one will become the 0, 2, 0, 2, 1, 2, 3, 4, F, 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 E, 0, 0, A, B, C, D. So that is where's the outcome they come from on the interface ID for the EUI 64. Okay, that is how they're going to be converted. So this one, you just have to make sure that the bit number 7, if you just shift, either it's from 0 to 1, 1 to 0. Whichever you receive is 1, then you shift to 0. Let's say you have the address already, your MAC address is have 1 over there. Then you just shift to be 0. When you have a 0, just shift back to the 1. That's it. But normally, they will get it as a 0, 0. Okay, what we get will always be 0, 0. Because 1 bit 1, it means that you have a global or they have a locals. So 0 is a global management address and 1 is on the local management address. So that's one is not very important for you to get the understanding, but you just have to make sure that this bit of 7 bit, you need to indicate either it's a global management address or local management address. But when you're doing this EUI, they will automatically just shift from 1 to 0, 0 to 1. This one, you need to know how to perform the changes, how to modify these changes. This you'll be asking into your written exam. They will ask you about on the EUI 64. Which one conversion is correct? Okay, they will ask on this question. Please be careful how they are conversion on the EUI 64. All right. And under IPv6 multicast addresses, okay, in the V4 multicast address is start from 2 to 4, 0, 0, 0 up to 239, 255, 255, 255. This is the range of the multicast addresses. But for IPv6, multicast address is always start from FF00 colon /8. Okay, so inside this is a F flag. The flag over here is that can be 000 or 001. Okay, permanent assigned well-known address or indicate a temporary address. So normally the flag over here, it should be zeroed. And the script, this is a script. Okay, this is script. The script can be 0, 1, 2, 5, 8, E, F. 0 is reserved, 1 is node lockers, 2 is link lockers, site lockers, organization lockers, global script, and the reserve. So that is on the combination we can provide under the scope. But most of the time, the scope they be using is either 1 or using 2. It's the node locker or the link lockers. Okay, link lockers means that if we in the link, node locker is between all the routers devices. Okay, so in between where are the scope they belong to, node or belong to link, and behind this XT bit must be 0. Okay, must be 0. This must be 0. And this 32-bit will be your group ID. The group ID you define into the multicast addresses. Okay, group ID. So let's say you have a 224.0.0.1, then you have a 1 or 2, 1 and 2. So let's say you have this FF, sorry, 00 colon 1. So that's one of the multicast address. You also have FF01 colon 1, FF02 colon 2 or colon 1. So it depends. They have different meanings over here. So that's how they represent on the. Sorry, this one it should not have. Okay, because 00 are reserved. You always have a 01 or 02. Because 0 as a reserve, you cannot have a 0 bit over here. Okay. Then followed by the multicast group IDs. How we're going to assign this ID into the multicast address. And this is where we look into how we're going to predefine the multicast address. There's some address is already permanently already defined like this. That's all the node lockers and also the link lockers. So normally we're using the link lockers. Node lockers is just between the devices, okay, between all the node and all the routers. Yeah, this is very similar to the 224.0.0.1, okay, and 224.0.0.2. Just that the location, the screw are different on the node lockers, and this is on the link lockers, okay, link locker, node lockers. So this is on the multicast address for the all nodes or routers within the link lockers, and we have a FF02.0.0.0 colon 1 colon FFXX colon XXXX. This is multicast address solicited nodes. This one, later when we go into the multicast, we're going more in depth on this, why and where they come up with this FFXX information. Okay, that will be a later part I'm going to mention on this. And like the OSPF in the IPv4 using 224.0.0.5, right, and 0.0.6. So in the multicast IPv6, they're using FF02 colon 5 and FF02 colon 6 as to DR and the for normal routers, for DR others. And for the all the multicast to all the PIM routers is using the D, yeah, D. So that is on the multicast address for the PIM routers. So that is how it differentiate on the predefined multicast address. Let's say you want to do it on the site locals, then you have a FF05 colon 2. Site locals for all the routers you receive this information. Okay, so you have link locker, node locker, or site locker. The site locker means that the private area, private addresses, okay, on the site lockers. So that is on the defined inside the multicast addresses, how they have already predefined. They also have a predefined by using a permanent address. The second 0 over here is called a permanent. Okay, it's a permanent flag. Okay, in this flag is only 0 or 1. Permanent or is a temporary. Okay, 0 or 01. So far, okay? Any questions so far? Before I go forward, how to map between the V6 address into your IP V6 multicast MAC address. All right. So for the mapping between the multicast IP V6 address, between V6 and multicast address, what are the difference between these two? So on the Ethernet, multicast IPv6 must be encapsulated into the Ethernet mode. Okay, that is what they are required. Okay, the destination IP address of the multicast IPv6 address is multicast V6 address, and the destination MAC address must be multicast MAC address, which must be corresponding to the multicast IPv6 addresses. So because of when you converted to be layer 2, they must be inside the Ethernet mode. They must match the MAC address. They must form a multicast MAC address in this case. So the 3333 is a MAC address prefix reserved for the multicast IPv6 address, and the last 32-bit of the MAC address are copied from the 32-bit of the corresponding multicast IPv6 addresses. So using the 32-bit multicast addresses map into your multicast MAC address. That's how they are specifying in this case. So you can convert to 3333. Okay, that is on the multicast MAC address, followed by 00000001. So it be 3 byte, 3 byte. So it will be created as a multicast MAC address. But how you know that? You remember that what's the requirement for the multicast MAC address? The first byte, last bit must be 1. So 33, how you convert the 33? Let me convert the 33 first. Okay. I will just convert it like this. Not enough. 33, the first byte, it be 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1. This is 33. Okay. The first byte, last bit, when it's 1, that is considered as a multicast. Okay, multicast. If let's say your multicast address is a FF02 colon 5, what will be your multicast MAC address? It will be 33, 33, 00, 00, 05. Okay? No, sorry. One more zero. 00, 00, 00, 05. Okay? Okay, that's my multicast MAC address. Let's say you are using the FF0205 colon 05. That is what you're getting. Okay, so that is how the conversion between the V6 address to become multicast MAC address. The multicast IPv6 to the multicast MAC address. Is that all right? Any questions so far? Okay, the next one is a solicited node multicast address. That's what just now I did not mention. They have added in the 01FF behind. So this is on the solicited node. The solicited node multicast address is generated based on the unicast or anycast address of the node. So when a node has a IPv6 unicast or anycast addresses, a solicited node multicast address is generated for the node. And the node join the multicast group that corresponding to the IPv6 unicast or anycast address. This usually happen when you work together with the unicast or the anycast. They're going to have this information. It's called solicited node multicast addresses. Okay, when they take part of the anycast question, anycast addresses. A unicast address or anycast address corresponding to the solicited node multicast when they are sent to the neighbor discovery or the DAD, a duplicate address detection. When these two happen, they're going to send this solicited node multicast address. Consider the prefix as a FF02 : 1. Okay, they have a colon FF : FF00 : 0 /104. So they're going to use the first 104 bit to consider this is a solicited node multicast address. And the last 24 bit of the corresponding IPv6 address will be the valid scoop, and the solicited multicast address is the link local scoop. This is only for the link local address only. Be in your link locals, be in your link. This is what they're going to send on the multicast address for the solicited node. So later for these functionalities, we're going to tell more when we're doing the ARP, when you're doing the neighbor discovery, and also we're doing the DAD. So they're going to use this solicited node multicast address to sending out their unicast address or anycast address to the neighbors to figure out what are the multicast address on the other side. Okay, to get the ARP, address resolution. There is a solicited node multicast address. Means that last time we can broadcast, but now we can't broadcast already. We have to use the multicast. So as I mentioned just now, what the things is replacement for the ARP broadcast, then over here there's the answer. They're using the multicast. Multicast is a replacement of the ARP request of the broadcast. So they're using multicast override the broadcast. Instead of they send broadcast into the IPv6, they send only the multicast. Whoever understand the multicast, you will like accept. Let's say do not know, you will not accept. Okay, that is what it means by the solicited node multicast address. When more in detail, I will show you into later part that how they send this multicast address by doing the ARP, neighbor discovery, and also duplicate address detection. So they're using this multicast address. And the last one over here is on the IPv6 anycast addresses. Under anycast address are the type of the address in the IPv6. Anycast address can be any address that you use inside your IPv6 address. And anycast address identify a group of interface that generally belong to the different nodes. A packet sent to the anycast address is sent to the nearest interface that is identified by the address. Okay, I will send to the nearest one. Anycast address are allocated from the unicast address space. Use any of the defined unicast address format. Anything is a unicast address, you can be act as the anycast address. They do not have a specific script for the IPv6 anycast. You can use any unicast address to become your IPv6 anycast. As long as your protocol they support, then they can be performed as a anycast address already. Okay, and therefore, when configure anycast address, you need to specify that is an anycast address. You need to tell that, oh, this address is used as anycast through the routing protocols. You have to define this address I'm assigned right now is meant for anycast purpose. So that is how we specifying the anycast address. Okay, the subnet prefix can be any. It's an n bit, so you can use any bit. Okay, so it means that you can use any unicast address to become the anycast addresses. All right, that is on the IPv6 anycast addresses. So far up to this point, for this address classification, any questions? Okay, address classification. So we have different type of addresses I mentioned just now. We have a unicast, we have a multicast, we have anycast. Inside the unicast, we have a link lockers, site lockers, unit lockers. We also have the global unicast. There's all the different type of classification of the IPv6. And next, we look into the basic protocols. What type of protocol they be used normally inside the ICMP, inside the IPv6 protocols? So ICMP is one of the common protocol we use. We need to use ICMP quite a lot. Okay. Later, after the lunch, come back, I will cover on the basic protocol as well as on the transition technology and so on. That's all the topic I've covered later part after the lunch time. So let's go for a lunch. Then come back, we continue with the basic protocol of the IPv6. All right, let's take a break. Okay, let's take a break from 12:30 to 1:30. We come back at 1:30 and we start for the basic protocols. All right, thank you.